Hi everyone, welcome to the lecture on nearest neighbors as part of the eGate.ai's machine learning lecture series. I'm Dr. Amrith Krishna, your lecturer for the series. So let's look into nearest neighbor classification. So let me illustrate it with the scenario that you can see here on the screen. So you can see there are few red dots and blue dots, and you can see there are three circles which does not have a color yet. So these are also labeled as A, B and C. I hope you can see all the three circles. So there are these three blank circles, and for a classification problem with two classes which are red and blue, we need to see what will be the colors for the points A, B and C which are not yet colored. So how would you color the blank circles? So if we base it on the color of the nearest neighbors, we would get A as blue, B as red and C also as red. This is based on the nearest neighboring data point or the color of the nearest neighboring data point. So here we can see that the training data partitions the entire instance spacing using the labels of the nearest neighbors. Nearest neighbors is based on the intuition that the points closest in a feature space are likely to belong to same class. So here we have to keep in mind that choosing the right features when designing a classifier is very important here. If we have the right set of features, then we have a feature space where the similarity or the closeness of these features can possibly mean that they probably should belong to similar classes. So I can state the same thing using distance as well. So the lower the distance or higher the similarity between two data points, they tend to be close, and then hence it is likely that they should have similar classes or they should share the same classes. Now if we look at the minimal or the most basic version of nearest neighbors, we can see the following. We see that the training examples are vectors xi along with the label yi. We simply need to store all the training examples. That suffices the learning. We just store everything. There is no other learning involved. For a new example, for an unseen example x, which is not in the training set, we find the closest training example xi that is closest to that, which is x here. We then assign the label or predict the label of the new one, which is x, to the label yi. And why is it yi? Because yi is the label associated with xi. As simple as that. So this is also called as the one nearest neighbor or one NN problem setting. So it's very simple. We have training vectors or training examples formulated as feature vectors. There is no learning per se involved other than just storing all the training examples, which are nothing but the vectors and their labels. For a new instance, we simply find the closest example and assign the label of the closest example. Now let's extend this one nearest neighbor to k nearest neighbors. So what is one nearest neighbor? We are assigning the label to a data point which is unseen during training based on its most nearest neighbor. Now, what if I can extend it to k nearest neighbors, or what if I can assign label to a new data point based on its k, top k, or the most closest k neighbors? Not just one, the k can be any arbitrary natural number. So here, the first two steps remains the same. The training examples are vectors, nothing has changed there. There is a label associated with each training example, nothing changes here. Learning is also pretty straightforward, just store all the training examples. There is nothing changed here. Now, for the prediction, instead of finding the one closest or the most closest one, we are finding the k closest training examples to the unseen one. Now, construct the label of x using these k points. So if it was just one neighbor or one nearest neighbor, it was pretty straightforward, right? Whatever that label is, just assign it, just copy it to a new unseen example as well. That's it. But now you have k points, and again, if all the k have the same set of label or the same label, if all the k have the same label, then again it's pretty straightforward. Just copy that, no problem. But life is not always that easy, right? So when we have k points, we have to account for a scenario where at least one or maybe few of them might have a different label than the rest. So now how do we handle such a scenario, which is quite likely that when we have different labels for the k nearest neighbors, which one to assign? Again, for classification, how would we do it? And for regression, how would we do it? This can be quite different because in classification, we have a categorical label. For regression, we have an ordinal and continuous number. So for classification, what we generally do would be that every neighbor votes on the label, predict the most frequent label among the neighbors. It's pretty straightforward in that sense, right? We just take a voting and the label with the maximum number of neighbors, or okay, let me put it this way. So the label that is most frequent amongst the k neighbors for a given instance forms the label of the instance. That's it. For regression, we generally predict the mean value. So k nearest neighbors are generally seen as an instance-based learning. It is a class of learning methods where the learning is pretty straightforward. It is just storing examples with labels. So in computer science also, we might have encountered this computation versus storage trade-off. So here, there is no computation per se other than just storing the examples when it comes to learning. And prediction, that is when presented with a new example, we classify the labels using the similar stored examples. And k nearest neighbors is one such instance-based learning algorithm. It is also called as lazy learning because most of the computation, or in more simpler cases like the one we've seen, all computation is performed only at the prediction time. Now, in k nearest neighbors, I think we have discussed the whole algorithm, which is pretty straightforward. We just find the k closest training examples and assign the label. And here again, just like previously, we had this ambiguity of what is the best or what is the closest. Here also, we need to have some definition or a clear empirical way to define closest neighbors. So we basically need to have a distance metric. A distance metric. Now the core, the backbone of so a similarity measure or the distance metric forms the backbone of such approaches, along with the definition of feature space, which is true for most of the other learning approaches as well. So I'm excluding the feature space definition here because it's anyway common to any classifier learning. So now we talk about the other part, which is a similarity measure or the distance metric. It forms a core component of this approach because that's what all we have in terms of computation. So depending on the domain and the task at hand, we need to be careful in choosing the right distance metric. And in a way, it is a good place to inject the knowledge about the domain. So how do we measure distances between instances? So with numerical features, when represented as n-dimensional vectors, we may simply use the Euclidean distance, Manhattan distance, or the norm. And when it comes to symbolic or categorical features, the most common distance that we use is the Hamming distance. It basically says the number, or basically tells the number of bits that are different, or the number of features that have a different value. It can also be called as the overlap. So in this case, we can see that there are 3 features. So the maximum Hamming distance can be 3, of which x1 and x2 has the same shaped triangle, but they differ in their color and orientation. So I will correct it here. I think I missed something. So this is a representation of 2 input data points x1 and x2, and we have 4 features. So the maximum Hamming distance possible would be 4. It so happens, so between x1 and x2, 2 features have matching values, 2 have different values. It's simple as that, right? Pretty simple. So we can say the Hamming distance here is 2 because there are 2 features where the values are different. Now if you look at the advantages of k-nearest neighbors, the training is very fast. Just adding label instances to a list, that's it, nothing else. So one may employ more complex indexing methods. It can slow down learning slightly, but can make prediction faster. So again, when we think about it, generally speaking, prediction needs to be faster as compared to training, because training generally happens at the back, as a back-end thing, as a one-time thing or a one-off thing. So prediction is most of the time that faces the customer or the client. So naturally, typically the predictions have to be faster in comparison to training. So in this scenario, well, what I just said about the speed of prediction or inference has to be faster than the training is true for any learning solution, not just for k-nearest neighbors. In the case of k-nearest neighbors, our training time is generally negligible. So when the size of the dataset really scales or really increases, it is quite advisable to use complex indexing methods or more advanced indexing methods. Even though it may slow down the training or the storage, it can make the prediction faster. And k-nearest neighbors in general can learn very complex functions. And we always have the training data. So this is very interesting. So we have seen both decision tree and perceptron. So in perceptron, we treat one data point at a time and we simply update the vectors. We simply update the weight vector based on the whenever there is a mistake made by the classifier. Assume we don't store the training instances. We use the training instances, we update the weights, and we dump the training instances. Now the algorithm will still work fine, but we will not be able to fully recover the training data if we need it. So if we have to have access to the training data, we need to store them separately. This is true for decision tree as well. In decision tree, even if you're doing batch processing, let's assume that after the training we delete the data, then it might not be able to fully recover the data. But in k-nearest neighbors, we are always storing the training data because that's the only thing in the learning. So if you want to do something with the training data later, for others, we explicitly have to have a policy to store it. But in k-nearest neighbors, it's pretty straightforward. That's the only step we do, which is storing the training data as is. Now, what can be the disadvantages here? So it definitely needs a lot of storage. So we saw that in decision tree, right? If I have say 100 features and even if they are binary features, I will still need to have 100. There is a possibility that there can be 100 power 2 unique vectors that can come up. So it needs a lot of storage. But is this really a problem now? Nowadays, with the storage being really cheap, I don't think this is a problem. In fact, not just about the cheapness, it's more about the ability to retrieve data first. So nowadays, it's not really a problem. But still, the prediction can be slow. So this is probably a requirement for many solutions. For example, if you have a streaming solution where you have large amount of data coming on a second by second basis, which is also another way of streaming, then prediction has to be fast, and prediction can be slow because all the computation or most of the computation happens during the prediction. So naively, the complexity here can be big of dn, where n is the number of training examples and d is the number of dimensions. And more data will just make it more slower, because when you're finding the neighbors, naively speaking, you have to go through all the data points, and in fact, again, the comparison has to be at the element wise or dimension wise. So you have to go through all the data points, all the dimensions of all the data points. So when you keep on adding more and more data, the prediction time increases. So compared to other classifiers where the size of the training data set after a certain point may not even matter, this one is not the case in nearest neighbors. Now, nearest neighbors are fooled by irrelevant attributes. So I think we discussed this in one of the previous slides, where we said that deciding the feature space or deciding on the features is of utmost importance, because the distance metric or the similarity metric is determined based on the on the features that it is defined on. So if we have irrelevant features, then it is very easy to have a misprediction or to fool the algorithm. So this is very important thing that we have to keep in mind. To summarize k-nearest neighbors, this is probably the first machine learning algorithm, and if there are enough training examples, the error of nearest neighbor classifier will converge to the error of the optimal predictor or the best possible predictor, but that number may vary. In practice, use an odd k. So that's very interesting suggestion. It might look very trivial, but it's a very interesting suggestion. And I think now you may be able to guess why is that the case, because if you have an even k and there is a possibility that for a classification task, there can be equal number of neighbors with different labels. Or say if it's a binary classification task and if k is 8, then I may have 4 and 4. And then the majority voting will not help. So to break ties, it is better to have odd number of uh, odd number of this neighbors. How to choose an optimal K? Ideally using a held out set or by cross validation. So this is one point. This is another point. Yeah. Feature normalization might be important. Often it's a good idea to center the features to make them zero mean and unit standard deviation. Because different features could have different scales, the distance weights them equally. Now, just like decision trees and perceptrons, variance exists for this one as well. So, neighbors labels could be weighted by the distance. That is one way to look at it. There are many other variants that exist. We will not go into the details. So once you get into IITs, make sure you take a machine learning or an advanced machine learning course where some of this might get covered. So thanks. So now I think we have 2 more lectures remaining, which is SVM and neural networks. Thank you.